Hello everyone, I am Saptarshi Mukherjee. I am currently a software engineer 3 at Google and I've been a computer programmer from over a long time. So in this playlist we are discussing the problems that appeared in Codeforces round 922, and in this particular video I'm going to discuss the problem D, blocking elements, which I found to be one of the best problems I've seen in the last few months from both a competitive perspective as well as an educational perspective. You get to learn a lot of concepts. So I would urge all the viewers to really pause the video at some moments, think yourself, and then see how I'm doing it. This is a very good problem to practice and grasp a lot of educational concepts. So, yeah, please do watch it till the end and try to code it on your own. It will improve your programming ability quite significantly by learning these concepts and applying them. Okay, so let us take a look. The question says we have an array of numbers, there are n numbers, and we can block some of those elements. So there are n elements, we can block some of those elements. How many elements? Any number of elements. We can decide that. We will choose some indices and we will block them. As a result of blocking them, there will be some cost. The cost has some definition. We have to minimize the cost that is given in the second line itself. We have to minimize the cost. What is that cost? The sum of the blocked elements and the maximum sum of the segments into which we are dividing the array. The maximum of both of these. So it is the maximum of these two things. One is sum of the blocked elements, another is the maximum sum of the segments into which we are dividing. So let's take a look using an example. The example is given in the first test case of the question. So the formula basically is, the cost formula is basically the max of the sum of the blocked elements and the max sum of subarray between two consecutive blocked elements, or we can say the maximum sum of subarray containing only unblocked elements. Yeah. Now let's take an example. The example given is 145332. I can block any elements. Let me make some copies. Yeah. So in the first case, let's say I block um, this element 4 and this element 3. Then what do I get according to the formula? These are my subarrays. This is one subarray, this is another subarray, this is another subarray. The sum of the blocked elements in total gives me 4 plus 3, which is equal to 7. This first subarray gives me 1. The second subarray gives me 8. This third subarray gives me 2. So I have to find the maximum of 7, which is the sum of the blocked elements, and 1, 8, and 2, which gives me eventually 8. However, if I mark in a different way, let's say I mark this 5, and or let's say I mark this 4 and this particular 3. That was also fine. Let's try that. I'll mark this 5 and this uh, 2. So what do I get? Over here, my summation is 5. Here the summation is 6. And the blocked elements, they sum up to give me 7. So I have to get the maximum of sum of blocked elements and 5 and 6, which gives me 7. So what do we see? That if I block in the first way, I get the cost as 8. If I block in the second way, I get the cost as 7. So which one is preferable? Definitely the one which is having lesser cost. That is my optimization strategy or my optimization objective. I need to optimize the cost, minimize it as much as I can. So 7 is the minimum cost that we see. In this example, you can try out other ways as well. This is the minimum cost. Question is how to find. So that is what is required in the question. I think we have to print the cost. Yes, how you are blocking it, etc. doesn't matter, but you have to print the minimum cost. Again, you can block any number of elements. Okay. Now, before we sit on a strategy, we have to first understand what are given in the question. Do we know which elements to block, how to choose the elements to block? We don't know. So first thing, we don't know how to choose the elements to be blocked. Over here, we can see that some maximum element we have chosen for blocking. There can easily be a case where choosing the maximum element will definitely not help. Where choosing the maximum element will not give us the right answer. We can create such example easily. For example, something like this: 1, 4, 5, 1, 5. Yeah. So if I choose the maximum element over here, uh, yeah, if I choose the maximum element over here, and then whatever I choose, my answer like this. I mean, if I choose this one and let's say this one, then my maximum will become 6. However, if I let's say choose this um, 4 and this one, then my answer becomes 5. If I only choose this two yellow elements, and if I choose the encircled elements, my answer is more. So definitely choosing the maximum or the minimum, that is not going to be a right approach. And it is, I mean, we have to make multiple choices, not just one element that we can apply some arithmetics. We don't know that. Second thing, we don't know what will be this cost. We don't know what will be this cost. So there are two things we don't know: how to choose the elements that will give me minimum cost. I have no idea what will be the minimum cost. However, I know that I have to minimize the cost, and the cost is formed by a maximization. Can you see? This is a maximization. By maximization, I'm getting a cost and I have to minimize that cost, which means I have to minimize a maximization function. And this kind of problems are referred to as minimax problems. Minimax problems. Another interesting part of the problem is if I block more elements, this particular part will rise, sum of blocked. If I block less elements, this part will rather rise. If I block less elements, then the subarrays will rise. So I have to choose a balance. And this is where decision making becomes tough. It is no longer an easy problem. So now going back, what we have just discussed is it is a minimax problem. And in minimax problems, a very popular strategy where we don't know what exactly or up to where we have to minimize, what will be the final thing. A very good optimization strategy is binary search. And we call that strategy as binary search on answer. So it's something like this, that when an array is given to us, if somebody tells us, hey, can you do it in cost something within 7 or something within 8? We can try with 7 or 8 in mind. If we have nothing, no goal, it becomes tough. Binary search on answer basically does a binary search to give us that kind of a clarity that, hey, try with 10, try with 5, try with 7, try with 8. Binary search on answer will give us those values, and we can try on those values and finally reach the best solution. How the best solution will be reached? Through binary search. But binary search on answer technique will give us the individual values which we can use as our temporary thresholds. We can see here the best threshold is 7. So similarly, we can use our temporary thresholds and finally reach the best threshold. Let us see how it is done. So over here, if we take this example, the question that we need to ask is, hey, let us say we are defining what is the cost. You have to tell me, is it possible? Is it possible to block elements? Is it possible to block elements such that the cost is less than equal to x. Which means that now I'm working with some x in mind. This is the question that I will primarily ask. And I will do a binary search on possible answers to decide. So I know my answer in this particular array, let's say, in the array that I had shown, 1, 4, 5, 3, 3, 2. Let us take this to the next page. One, 4, 5, 3, 3, 2. We have seen that the best we can get is 7. We don't know that. What will we do? Binary search will say, hey, your answer will lie in some range. Over here we can say your answer basically lies in some range 1 to the maximum. What can the maximum cost be? The sum of the array, we can say. There can be other numbers as well, but you can just take something like that. The answer cannot be more than the sum of the array. So the sum of the array is 10, 16, 18. We can take 1 to 18 and then we can say, hey, the answer is somewhere in 1 to 18. So start with the mid value. The mid is 9. Is it possible with 9? With 9, is it possible to block the elements? We have to do some computation with 9. And we know over here with 9, the answer is yes. Cost less than equal to 9 is possible. So if cost less than equal to 9 is possible, if this is possible, that means cost less than equal to 10, less than equal to 11 definitely are possible. I want to minimize the cost. So I will say, okay, 9 is good. Can we do in lesser than 9? We'll ask this question, hey, can we do in lesser than 9, which means in 1 to 8? This is binary search. We are trying with one value, the mid value, and we are doing some computation. How we are getting this yes, we will answer that after around 5 minutes or so. But before that, let's figure out, let's say we know how to answer this question. Then, by applying different values of x, how to find out, that I am showing. This is the binary search. By applying different values of x, we will find out the answer. So this is your first value of x. The next 1 to 8, so the mid will be equal to 4. And when mid is equal to 4, the answer is the cost less than equal to 4 is not possible. We can just see this 5 is greater than 4. In this way, anyway, whatever technique we use, we will be able to find out. This is not possible, so we will say no. No means lesser than 4 also definitely it is not possible. So I have to go higher than 4. Already I am searching up to 8. So now I'll go bigger than 4. I'll say from 5 to 8, let's focus. So what is the mid? Mid is 13 by 2, which is 6. And what is the answer for 6? For 6, we know that the cost is not possible up to 6. We have seen that. So the answer is 7, we know that. So in some way we'll find out, hey, it is not possible. So then we will try, okay, greater than 6, 7 to 8. What is the mid? The mid is equal to 7. For 7, we'll say, yes, it is possible. We know. And then we will try, okay, mid plus 1. 7 plus 1, 8. 8 to 8. Mid is equal to 8. We will say, no, not possible. That's it. So this is the last element. Now, lesser than mid, nothing is left. 8 to 8 was the only range. So in just 5 comparisons, what have I got? The last yes gives me the answer. The last yes gives me the answer, that is 7. What did I do? I did not ask for 7 purposely. I basically followed the path of binary search. Binary search ensured that if the answer is somewhere here, if we are maybe first asking about this, then we will go to the left. Then if we ask about this, then we will go to the right, and so on. We will reach closer and closer to the best answer. That is what binary search and answer will guarantee. So over here, what do you see? That if we know that for a given target, whether we can reach that target or not, then what is the best target, we can easily find that out. We don't have to go linearly. We don't have to say, okay, try for 100, then 99, then 98, then 97. No, we just have to do only 5 steps in this case. And binary search, as you know, works in log n time. So if our range is, let's say, so basically the time complexity of this much will be big O log of range iterations of binary search. Iterations of binary search. Okay, this particular technique you can see in many interesting problems like book allocation. You can see in painter's partition problem. Book allocation problem, that is the minimum number of pages that a person has to read. So there are consecutive books, and every person, there are n persons, every person will read some consecutive books. So the minimum number of pages one person has to read, that is that book allocation thing. And painter's partition problem also, the minimum time needed by one painter, where I mean there are these you know, cardboards or whatever to be painted, walls to be painted or whatever, and then the lengths of the walls vary. You can look up these problems. These are very good problems, or very common problems, you can say, on binary search and answer. But the best part of this particular problem is this only solves part of the problem. Now the main is, how can I answer this question? Binary search on answer basically says that if you can answer this question, then I can ask for different x and get you the best x. Best x is the cost. And there is a particular thing. In this particular problem, we know that if cost less than equal to 9, if cost less than equal to 9 is possible, makes it possible, that means cost less than equal to 10 is also possible. Cost less than equal to 11 is also possible, and so on. So whenever you have that kind of a thing, that if x is possible, then x plus 1, x plus 2, they are all possible. If x is not possible, then x minus 1, x minus 2, they are not possible. Then only binary search can work. And that particular property, we call that as monotonicity. We call that as monotonicity. That is, in our range where we are searching the cost, if there is this trend that up to the answer or before the answer, it is not possible with those values. Cost is not possible to be there. And from there onwards, cost is possible to be less than equal to each of them. So easily we get that kind of a pattern that, hey, is cost possible to be less than equal to 9? If I hold 9 as the threshold, can I block few elements and get the answer? Yes, the answer is yes. If you hold equality, it will not hold. So you have to frame the question in such a way that it is a monotonic thing. Less than equal to 9, less than equal to 10, less than equal to 11, it will continue. So yes, cost less than equal to x is a monotonic approach. Okay, you can look up these two problems to gain further insights. Now going to the next part, which is how to answer the first question. Is it possible to block elements such that cost is less than equal to x? So I'll copy the question once again. Yes. And now, so let's say this was our array 1, 4, 5, 3, 3, 2. Now I don't know which ones to block. I don't know which ones to block. But let's say I will block this. So you might have seen this. There are many problems where we may choose or may not choose. So we say, okay, by choosing what is the best we get, by not choosing what is the best we get. So over here, let's assume that we are choosing this. We will choose this. Let me name the indices 0, 1, 2, 3, 4, 5. If I choose this, now what should I choose before this? What should I choose before this? What is the previous element that I should block? Let's say I block this, then what is the previous element? Can I block this? What can be the previous element? This can be my previous element. How can I decide? I can decide that, hey, between these two elements there is nothing. So the subarray less than equal to x is not violated. This one, can I choose this as previous? This one I can choose. Can I choose this one? Yes, because what lies between this 3 and the last is less than equal to x. So what x we are going forward with? Let's say x is equal to, let's say 6. So for x equal to 6, I'm trying. That okay, for 2, what am I trying to find? That, hey, for 2, what is the best answer? If I choose this 2, what is the best answer? So I'm saying, hey, I can, before this 2, I can choose this 3, because between this 3 and 2, only 3 is there and 3 is less than x. So definitely I can choose this 3 as my previous blocked element. I may or may not choose. Can I choose this one? Yes, before 2 I can choose, this can be my blocked element before 2, because this portion is less than equal to x, and so on. Can I choose this one? 4, can this be my previous blocked element? No, because the elements over here, 5 plus 3 plus 3, is greater than the x. It is not less than equal to x, it is greater than x. Which means that I cannot choose this. This cannot be my previous blocked element. The previous blocked element has to lie somewhere over here. The previous blocked element has to lie somewhere over here. It cannot lie before that. Right? Now, if I know that on choosing this one, what is the answer up to this one? On choosing 5, what is the answer up to here? Let's call that as answer, or let's say value of index 2. Value of index 2. If I know that, okay, that on blocking this one, what is the answer of this one? What is the answer up to here? What is the answer? Answer means, answer, let's say, is the minimum sum of blocked elements. Why? Because we have to block so many elements. So I'm saying minimize the number of blocked, minimize the sum of blocked elements by keeping the subarrays, each subarray sum under x. So I'm following that strategy. Let's say for this 3, the answer is v3. And also let's say for this 4, the answer is v4. For this one, I don't know what is v5. But if I know v2, v3, v4, v1, v0, if I know them, can I say that v5 is basically equal to, v5 means I am choosing that element. That means a5, or capital A5 plus the minimum of v2, v3, v4. What is v? V of I is equal to the minimum sum of blocked elements in 0 to I such that AI is blocked, AI or I, whatever you say, that is blocked, and every subarray unblocked has sum less than equal to the x. So subarrays I'm basically saying, so I'm sitting at the end, I'm saying, hey, if you choose me, what should I do? I should say, okay, my previous element can be any of them. Which one should I choose? The one that will give me the lowest sum of blocked elements. Why? Because if each guy, if that 5, if that 3, each guy, if they try to minimize the sum of blocked elements, then finally what I'll have, that is the minimum sum of blocked elements possible. And only when I try to minimize the sum of blocked elements by keeping the subarrays happy, then only my minimization, the cost optimization can happen. So that is the strategy, that hey, try to minimize the sum of blocked elements, because we are doing that step by step. And for that, let us assume that we are taking this element. If we take this element, now the previous element cannot be anything. Like for this, if I choose this one, previous element cannot just be any of these. No, I cannot take these two as my previous element, because this part will become quite heavy. This part will become quite heavy. This particular thing will not hold for x equal to 6. So I will only choose those elements, for which the subarray sum in between is going to be less than equal to x. All the elements are positive, that is given in the question. So we can say that it will be a continuous subarray. Before that, nothing is possible, and in this subarray, everything is possible. So I will take the minimum one, right? So mathematically, we can put it as Vi is equal to Ai, small a, capital A, please pardon that, minimum of Vj, where j belongs to where j belongs to 0 to I minus 1, such that the sum from j plus 1 up to I minus 1 is less than equal to x. There is one caveat over here. Maybe I don't need a previous blocked element. My previous entire prefix of the array can be sufficient to stay in a subarray. Like if the entire thing was less than equal to x, why would I take another element? So for the ease of calculation, often we put a 0 before this, so that if everything over here can stay as a subarray, I will just say to block this 0. So often what we do is we add a 0 before it. Often we add a 0 before it. And make it somewhat like this: 145332, 145332, preceded by a 0. Sometimes we add a 0 at the end, and then we say, hey, for this 0, find out if I block this, then what is the best we can get. This can say, hey, I will choose maybe this one as my best partner, and this one will choose maybe this one as my best partner, and that's how we will get 7. This may happen. So this one will say, hey, this will be my previous one, and this one will say this will be my previous one. So anyway, what we are doing is basically we are adding zeros at the beginning and end. 0, 1, 2, 3, 4, 5, 6, 7. So we have added these zeros so that I take that possibility also. Let's say I'm trying to find for this, or let's say I'm trying to find for this 5. Before this 5, there has to be no blocked element. So this 5 will ask this 0 also. Hey, can you be my previous blocked element? And 0 blocking 0, not blocking 0 has no difference. So we'll say yes, block this, so that what is in between, that is fine to stay in between. That is less than equal to 6 or less than equal to 7, whatever we were checking. So yes. So sometimes adding 0 before and after makes sense. Now let us solve a problem. By the way, how do we find this out? This particular sum, we can easily find this out using prefix sum. We can easily find this out using a prefix sum array. How? Prefix sum of I minus 1 minus prefix sum of j will give us the above solution. So if prefix sum of I minus 1 minus prefix sum of j is less than equal to x, then I will consider that j as a candidate for my previous blocked element. So what does each element do? To every element I say, hey, ask your previous elements what their best answer is, up to them, and then take the best that you can from them. In what terms? What is the best over here? The minimum sum of blocked elements till now. So every guy says, hey, up to you, what is the minimum sum of blocked elements? Okay, if I have to choose myself, I will make the sum of blocked elements the minimum I can, so that at the end we can have the benefit. We can basically at the end we will try to keep it as minimum as possible, and if it is inside x, we will win. So let us see for two different examples. For 6 and 7, the same array. So I have put zeros at the beginning and end. We will keep that. We'll adhere to the same convention. 1, 4, 5, 3, 3, 2. Yes. This is my array. Now you can use prefix sum for your calculations. I am not writing that. This is the V, and what you can see over here is that the Vi depends on the previous Vj's. So V of 5 over here depends on V of 2, V of 3, V of 4. Similarly, V of 2 depends on V of 0, V of 1, and so on. So basically, uh, if basically one state, if you consider V5 as one state, that depends on the other states. You can obtain the answer from the answers of those states. This is known as optimal substructure. This particular thing, when your Vi is dependent on Vj, Vj plus 1, and so on up to Vi minus 1, this particular thing is known as optimal substructure. Then another thing is, for this we need the value of this V4. Similarly, okay, for over here, let's say V of 5 depends on V of 3, and V of 4 also depends on V of 3. V of 4 will also ask V of 3, hey, you can stay before me. So V of 5 and V of 4 both depend on V of 3, correct? You will find many examples like that. So V of 5 and V of 4 in the above example both depend on V of 3. So when two different subproblems, two different states depend on the same states, of course they depend on other states as well, but when they depend on some common states, then that becomes an instance of overlapping subproblem. That becomes an instance of overlapping subproblem. When we have both of them, that gives rise to dynamic programming. When I have both optimal substructure and overlapping subproblem, that gives me dynamic programming. But that is a theoretical perspective. From a different, easier perspective, what we can say is, if we can express the answer in the form of indices, where the final index, I can say that this V of I, V of 7, blocking the last one, what is the minimum possible, that gives me the best answer. So when we can express the answer or a significant part of the answer in the form of an index, and those indices are then dependent on each other, not in a cyclic way, but one depends on few, they depend on few others, and so on. When this kind of a dependency of states comes in, that is a DP problem. So for a DP, it is important to find out how we can express the problem in the index form, as in the form of indices, and then one of them will give me the final state, that is the answer, and they are then dependent on other states and so on. That is dynamic programming. In every problem, if you can basically represent it in that form, you have cracked the problem. So yes, when we basically see, okay, this V is a DP array, this is a dynamic programming array, we often name this as DPI. So DPI is equal to Vi is equal to AI plus min of DPJ. So we name that array as DP, that is a convention, you can say. Okay, so over here, I will write the array as DP. DP basically means the minimum sum of blocked elements up to an index, such that the intermediate subarrays of unblocked elements do not cross a particular x. We will first do it for, let's say, x equal to 6. So we can say that the first one here, over here it is 0 if I choose this. If I choose this 1, it is 1. If I choose this 4, what can I say before 4? I can choose this 1 also, I can choose this 0 also. Subarray sum I'll calculate using prefix sum. So I can choose both of them. Which one will I choose? The minimum of these two. I'll choose the minimum of these two, which is 1. Sorry, 0. So 0 plus 4. 0 plus 4 gives me 4. Now comes the next one. But okay, when this 5 comes, here the subarray sum, so again 5 will be happy with all of these 0, 1, 4. Let me write down. So in this case, it will be 5 plus 0 is 5. And for 3, let's say for 3, we are going to calculate now. So for 3, are all of them candidates? Can I take all of them? dp of 0 to dp of 3? No. Because if I, let's say, choose this 3 and this 0, if 0 becomes my previous blocked element, then 1 plus 4 plus 5 is greater than 6. I can't do that. So I can't go up to there. I can say, hey, 4, oh sorry, I'm looking for that 3. So 3 can tie up with 4, can tie up, it cannot tie up with 1 because 4 and 5 are very heavy. So it can tie up with 5 only. So 5 is the only possibility. I will say definitely if, before 3, if you are choosing 3, then before 3, 4 should come. 5 can also come. So basically, okay. So 4 and 5 can come. If you choose 4, let me check. If you choose 4, that means this is your subarray, which is a valid subarray. If you choose 5, then this is your subarray, nothing, which is a valid subarray. So, but you cannot choose this one. For 3, you cannot choose this one. You can choose the 4 because within between 4 and 3, it's only 5. You cannot choose that one because 4 and 5 itself are very heavy. So, this 4 and 5 you can choose. You will take the minimum of them and add dp of, we have discussed, dp of I is equal to a of I plus minimum of dpj such that j plus 1 up to I minus 1, the summation has sum less than equal to x. So over here we are following x equal to 6. So let us see what we get. We get the minimum is 4, so 4 plus 3 equals to 7. What is the minimum? Minimum basically means that, okay, if I choose this 4, that means up to there my sum of blocked elements is 4. I can't go behind, then my subarray logic, subarray condition will get violated. So I have to take this 4. So 4 plus 3. 4 plus 3 gives me this 7. Okay, next. What about this 3? This 3, I can say, okay, this particular 3 is valid, which means this 5 is valid. This 5 will be valid. But previous 4 will not be valid because this 5 plus 3 is too much. So, okay, this 5 and 7 are valid, among them the minimum one. So 5 plus 3, 8. This is big. Then 2. For 2, what can I say? Again, 3 plus 3, 6 is the best we can go. So these are my possibilities. 5 plus 7 plus 8. We can take them. We get 5 plus 2 equals to 7. So subarrays are all in control. Now for 0, I will basically say, okay, for 0, what is possible? For 0, this is the maximum I can go. 3 plus 2, 5. So this is the maximum I can take. 7, 8, 7. You can do at your own pace. 7, 8, 7, the minimum is 7. 7 plus 0 is 7. So my minimum sum of blocked elements will be 7. But that is greater than x. So x equal to 6 is not possible. X equal to 6 is not possible. But if you do the same thing for x equal to 7, if you do the same thing that I did above for x equal to 7, you will see you will get almost the same dp states. And finally you have 7, and 7 is less than equal to x, which is 7. So the answer 7 is possible. So in this way, for different values, you can find out whether it is possible or not. We are interested in an inequality. Checking for inequality often is far easier than checking for equality. And that's why the strategy. This kind of a strategy of deriving from the previous dp states is followed in a lot of problems. A very common problem is longest increasing subsequence. LIS. Longest increasing subsequence. There we can, there we definitely don't have all the characters of this problem, all the characteristics of this problem. There we optimize in a slightly different way, but there also one element, the LIS, we calculate, let's say it ends over here. If it ends over here, then what is the maximum LIS we can get. LIS we can get. So and that depends on the previous LIS values. So it's a very common DP strategy. Once you get a hang over it, you can apply it in many different problems. Now the big question is how to get this minimum. This is the final remaining question. How to get this minimum. So you know that before you, up to a certain point, the elements are all, you can take those elements. And observe this. Initially for this 4, the window was this one. From here you could take anything. For 5, the window is 0, 1, 4. For 6, for this 3, the window is something like this, 4, 5. Then for this 3, the window has become, I think, 5, 3, yeah, 5, 3, right? This 5, 3. Looks so. So basically, can you see the window is progressing? The window is going forward. Then you have this particular window for the next one. You have that particular window, and so on. The window progresses. And what I'm interested in is the minimum in that window. So first you had this window, then you can see I had marked over here this yellow line. So you had this window, I needed the minimum, then I needed the minimum from this window, then I needed the minimum from this window, navy blue line, this window. Then somewhere I needed the minimum for this window and so on. So when I need the minimum in some windows, in some ranges, what are the techniques I can use? The prefix something will help me slide, will help me find out the windows. So what I can do is initially I add this window, then I will, when I come to this 3, I will strike out these elements and then this becomes my window from here to here. So in this way, from the prefix sums, I can find out the windows. I'll show you the coding implementation. So we can figure out the windows. But then in that window, in that range of indices, what is the minimum? How can we find that out? Some cliche techniques are using some advanced data structures like segment trees to find min of a range. Also, just to find the min, since from the left we will delete these elements, we will say, okay, forget this 0, forget this 1, then forget this 4. When we are progressing the window forward, that deletion and addition from the later point, deletion from the front, addition from the back, that thing can also happen in set. So that thing can also happen in set or map to tell the min. What else? In this kind of a problem where we are slashing elements from the left, depending on that prefix, some kind of computation, and where we are only interested in the minimum elements, either only the minimum or only the maximum, that's what we are interested in. We have a very popular technique in place known as monotonic queue. I won't stretch the video long, but this is an excellent concept to close this kind of problems. So I'll show how this happens, and you can then look at my code and you can study it more. There are some very good problems based on monotonic queues. For example, the next greater element of every element that is based on stack. So monotonic queue will help you solve the problems like, I think, minimum element. So you have some DQ based problems. There are some policeman thieves problems you will get, which was once asked to me in D. Shaw interviews. And then there are some very common problems. Yeah, the minimum in a sliding window. I think that only you have to copy. So the minimum in a sliding window basically is that what is the minimum element in every window of size m, in an array of size n. That exactly we are actually copying over here. Okay, that exactly we are copying over here. You can basically read that and do that. I'll show you a glimpse to basically complete the flow of our solution. I'll take a different example. Let's say this 0, 5, 2, 1, 4, 2, 3, 0. I've append prefixed and suffixed with zeros. I'll calculate this dp and I'll maintain the q. And this q, you will see, will help me get the minimum. So let us see. First dp of the first element is take me, nothing before me, so 0. I will add this 0 over here. Okay. Now, from this part, I am going to add. So things will come here, then here, then here, and so on. This is a queue. Add from the back, delete from the front. Then I have 5. For 5, I can say, hey, look at the front of the queue, you have 0. So it is 0 plus 5 equal to 5. Okay, what did I do? I basically said 5 plus 0 gives me 5. Then, what about the next element? Next element is 2. Okay, before that I'll add this 5. I'll add this 5 over here to the right. Next element is 2. 2 says, hey, I will take the first element. You will do that prefix some calculation. That okay, between me and that element, only 5 is there. Let's say we are considering our x equal to 5. Okay. Let's say we are considering x equal to 5. So for 2, we will say, hey, there is 5 over here, so it is valid. No need to do anything. I will take this one. This is the minimum one. I'll take this one. The first element of the queue, that is the minimum. Okay. So we are getting 0 plus 2. 0 plus 2 gives us this 0 plus this 2 gives us 2. Gives us 2. And when this 2 comes, now we can say, hey, this 2 will now get added. When this 2 gets added, it sees that there is a greater element. When it sees there is a greater element, 2 will say, hey, after this, whatever will come, if they get you, they will get me also. If they get 5, they can get 2 also. And 2 will be preferred because 2 is better. 2 is having a better answer. So 2 will immediately thrash away this 5. 2 will say, hey, from the end of the array, if there are elements that are worse than me, remove those elements. If there are dp values that are worse than me, remove those dp values. Enforce the minimum values. 2 comes. 2 also compares with 0, but 0 is better. So 0 is kept as it is and 2 enters. Now there are 2 elements in dp that we are interested in. 0, 5, 2 are were the 3 elements. We are interested in only 2 dp states, 0 and 2. And then what do we see? For 1, we will basically say, hey, for 1, again compare with 0, but before that you have to check the whether between 1 and 0 this follows the condition or 5 plus 2 doesn't follow the condition. So you will pop that out. You will say, okay, you are not eligible for me. I cannot take you as my previous element. That means none of my next elements can take you as the previous element. The sum has increased so much and it is only going to increase. So your job is done. You will not be taken as the immediate previous element. So this one is now removed. For this 2, when I'm handling this 2, this one is removed. Then what can I say? Okay. Then I read this for this 1. For this 1, that 0 is removed. Now I can read, okay, for 1, what is the first element then? That is this 2. So 1 plus 2 is 3. Between 1 and 2, there is nothing. That is fine. So 1 plus 2 is 3. 3 is not as good as 2. So 3 comes after 2. Then 4 comes and 4 is happy with 2. So 4 will say, hey, 4 plus 2 equals to 6. You can see this is going from left to right in an increasing order. So the leftmost will always be lesser, will always be the minimum element. So just read the leftmost point. This is what is called a monotonic queue. Next, come to the next element, which is 2. 2 gets added to 2 can give you 4. For that you need to check between 2 and 2. Is it 5? Yes, it is 5. So 2 again catches hold of this 2 and gives rise to 2 plus 2, 4. Next 3. What does 3 say? 3 says, okay, when this 4 comes, 4 will say, hey, 6 is no longer needed. 6 is no longer needed. 4 will thrash 6 out. That's it. Then comes finally 3. 3 will say 2 is quite far away. 1 plus 4 plus 2 is greater. So let me use a different color. So 3 will basically say, I can't tolerate that. Remove that 2. 3 plus 3. Let us see, 4 plus 2 is 6. No, this one is also not valid. So 3 will also throw this particular 3 out. Then it comes to 4. And 3 says, yes, I can take this 4 because this 4 comes from here, and between 2 and 3, there is nothing. So 3 plus 4 equal to 7. Now the last one. Last but not the least, 0 asks, hey, which one can I take? Can I take this 4? Yes, between 0 and 2 there is only 3. So 4 plus 0 is 4. So the minimum is 4. You can see if I would have taken this 7, I can't get the answer. Sorry, if I take this 3, basically I can't get the answer, because then the best answer is 7. This tells you, actually, this array tells you that by taking each element, what is the best answer. And at the end, 0 tells us that, hey, take this 0 and then take anything. And then the best answer is 4. From here, this 4 is coming, the minimum. Again, the front of the queue. So yes, 4 is less than equal to 5, which means that 5 is valid. Which means here, 5 is valid. We can say, how this 5 came? 0 came from this 4. So we can say it came from this element. 2 came from this particular 2, right? So we can say this element. Yes. Just by blocking these 2, we can get the answer. Just by blocking these 2, can you see? This is the minimum sum of blocked elements. By just blocking these 2, we can get the total cost within 5. And 5 is the best answer over here. That's it. In this way, this is basically your monotonic queue. This is basically your monotonic queue. This is quite a concept heavy session thanks to this very good problem of Codeforces. I'll show my code quickly. I'll go to the main function part. There you go. So this is the structure where I've basically maintained that queue. So it's a D queue because insertion, deletion are happening at both the ends. At least deletion is happening at both the front and the rear. So I'm using a D queue, double-ended queue. So this, while low is less than equal to high, this is my binary search. I have fitted my low as max because my maximum element in the array, the cost cannot be better than that. The cost cannot be lesser than that. So that I'm taking as a lower bound, and I'm taking some upper bound which is very large. I know it's logarithmic, so that's how I'm proceeding. And now inside this, I am testing. I'm basically trying for every mid value or x value. So this is my mid, and for this mid, I'm basically checking over here that, hey, is the diff greater than mid? Diff means the difference between the two blocked elements, difference of the subarray. So if the difference is greater, I will just poll, as I was doing. I was polling first. I was polling from the left. So that's exactly what I'm doing. From the left, I'm polling. And otherwise, I will basically take the first element for which the difference is fine. And that first element is the basis of my calculation. I will calculate my dp value based on that. dpi is based on that dpl. Okay. Now next, while mq.size is greater than 1, so I'm basically polling from the last. So before I'm inserting dpi, I'm basically saying whatever is greater than it, remove from the end, as we have seen already. And then if I see that yes, this is holding true, the condition is good, then I'll say, okay, try a better thing. This is your answer, now try a better thing. So I will make the high of the binary search range lesser than mid, and I'll try that out. That's it. So you have three concepts over here. You have a binary search, enclosing, a dynamic programming, where we are using monotonic queue to calculate those dynamic programming states efficiently. That's it. So I hope you have gathered something, gathered some good information. This was a very good educational problem from which whatever you have learned today you can apply in a lot of different problems. So I hope that you will be able to practice on these concepts and apply them in your upcoming programming contests. Take care, keep coding, and let me know how you felt about this problem. Please share with people who might find this problem, this discussion insightful and will be able to benefit from this. And let me know in the comments if you have any doubts about this problem or the later problems or before problems or any other contest problems. I'll be very happy to discuss. We can chat on LinkedIn or other platforms as well. And I have pasted my Codeforces and LinkedIn links in the description. See you all on these platforms. Keep coding and please like, share, subscribe if you feel the video informative. Thank you.